Hi, my name is Bishak from CSC department. I'm currently pursuing BE Computer Science final year. My project title is a lightweight REST-based multi-access edge computing framework for 6G networks. Yeah, introduction. 6G networks are expected to support ultra-low latency, high reliability, and massive connectivity for next-generation applications such as XR, autonomous vehicles, smart manufacturing, and real-time healthcare. Despite the advancements in multi-access edge computing, most current deployments rely on heavyweight orchestration and virtualization frameworks such as Kubernetes and NFV which introduce significant control plane overhead and resource consumption. To address these limitations, this project proposes a lightweight, REST-based MEC framework that eliminates dependency on a full-scale orchestration platforms and enables direct, efficient service management at the network edge. Our statement of the problem is the core problem lies in high control plane overhead, complexity, and inefficiency of existing multi-access edge computing frameworks, which limits their ability to support ultra-low latency and resource-efficient services required by 60 networks. Heavyweight orchestration dependence. Most MEC deployments rely on platforms such as Kubernetes and NFV which introduce multiple control layers, background services, and scheduled pipelines that increases latency and startup delays. Non-deterministic service instantiation, multi-stage orchestration workflows result in unpredictable service of startup times, making short-lived or real-time 60 services inefficient and unreliable. This project addresses these challenges by introducing a lightweight, REST-based MEC framework that simplifies service management, reduces control plane overhead, and enables transparent, low latency and execution suitable for future 60 edge environments. Scope of the project. Our focus areas: design and development a lightweight REST-based MEC framework for 60 networks, implementation of REST APIs for edge service lifecycle management, integration of edge level monitoring for latency, response time, and resource usage. Target audience: 60 edge computing scenarios requiring ultra low latency and high reliability. Deliverables: a functional REST-based MEC framework prototype, REST APIs supporting edge level service lifecycle management. Scope of the project inclusions: lightweight REST-based MEC service management framework, edge-level service registration, deployment, and invocation. Simple and efficient edge service execution model. Exclusions: no Kubernetes or NFE MANO based orchestration, no hardware accelerator edge processing support, no cross-domain or multi-operator orchestration, no end-user application layer implementation, um, no stateful service migration between edge nodes. Methodology: requirement analysis, framework design, and workflow modeling, REST-based MEC framework development, edge service deployment, monitoring and backend integration, testing and validation. Methodology: REST-based MEC service workflow includes defining edge service parameters, setting services access and invocation rules, assigning service endpoints and roles, deploying lightweight REST service logic, monitoring, updating, and managing service status. Edge-based data processing includes collecting service requests and edge node data, choosing process location, building a lightweight service data model, executing REST-based service workflows, implementing validated updates across edge services. Our architecture diagram or flow, our use case diagram here, our class diagram. Our sequence diagram is presented in our PPT. Kindly refer it for your future reference. Our algorithms used were lightweight REST-based service lifecycle management algorithm, acts as a core execution engine of the lightweight MEC framework, uses services descriptors and edge node resource availability to perform fast deterministic deployments, eliminates heavyweight orchestration layers to reduce control plane overhead and startup latency. Examples of region-based loan and verification patterns: low latency request, direct REST invocation, immediate service response, resource constraint nodes, lightweight runtime control, minimal CPU and memory usage, concurrent workloads, simple load routing with request level performance monitoring. Algorithms used: service registration layer, node selection and deployment layer, request routing and invocation module, performance monitoring and metrics engine. Filter service latency, CPU usage, memory consumption, and request status to generate real-time monitoring dashboards and benchmarking reports. Processes services inputs such as name, version, endpoint path, and resource hints to register edge devices into standardized service repositories. Maps register device services to available edge nodes based on CPU availability, memory capacity, and runtime readiness for fast deployment. Hardware and software selections. Hardware element processor, RAM, storage are dual core, minimum 4 GB, 120 hard disk. Software environment. Our operating system includes Windows 7 to Windows 11, Mac OS or Linux. Front-end languages includes JavaScript, JSS, HTML5, CSS3, JSON. Backend languages are JavaScript, Node.js, Express.js. Our database uses MongoDB and Mongoose ORM. Implementation. The system was implemented using a modular REST-based architecture that separates service registration, node selection, request routing, and runtime control for efficient edge computing execution. Front-end dashboards were developed to manage service deployment, invocation monitoring, performance visualization, and node status tracking across distributed edge environments. A lightweight service lifecycle engine was integrated to handle registration, deployment, startup, shutdown, and termination of edge services without heavyweight orchestration layers. Database structures were designed to store service metadata, node profiles, deployment records, metric logs, and benchmark results, ensuring secure and responsive data access. Our important code segments are basic fast API service invocation approach, that's a Python code, def invoke method, unwritten. Our MEC prototype main application routing from fast API import fast API. We are connected to the fast API, so Python, using Python code. Our test cases are included in this PPT. Kindly refer it for future reference. Research. The system successfully automated student financing workflows by generating personalized financial models based on academic performance, trust score, mentor validation, and institution level data. Conclusion. The proposed framework delivers lightweight REST-based edge computing architecture that enables low latency service deployment and efficient resource utilization for emerging 16 networks. So overall, the system provides a future-ready MEC solution that supports next generation 6G application through lightweight design, REST interoperability, and distributed intelligence. Our references are attached in this resume. Kindly refer for future reference. Thank you.